Welcome back once again to the third installment this time of the 6034 Fall 2020 review sessions. Today I'll be talking about the following three topics to last review session, which was role-based systems and Bayes. Today is K-nearest neighbors, ID trees, and neural networks. And without further ado, right on to question one. So here's question one. You know the drill. Pause the video here. Feel free to read through the information and digest it, and I'll just go ahead right into this question. So what we have here is we have a set of features and a set of values for a few data points, and the protagonist of the story is trying to use those features according to how similar they are to some new data point in order to determine the classification of that unknown or new point. And what I want to bring your attention to is, so we're asked for the best distance metric, and the way we would, if we were to plot this, right, how would we do so, because we don't have numerical values here. And I think that's a really key point in eliminating Euclidean and Manhattan distance, and that also to some extent eliminates cosine distance. So but I wouldn't really trust it trust selecting Hamming distance just yet. First, what I need to think then is, how is the classification being determined, or how is it determined? And what determines the classification in this case is how similar is it to previous inventions whose features are non-numeric. And I think that entire description is what would tell me, oh, this is Hamming distance, or the most appropriate measure in this case is Hamming distance. And that is also the explanation for the explanation box right below the question. So I'll just move on. Pause the video here and read through the prompt as much as you need to. I'll just continue with question 1.2. So with question 1.2, there are a few key statements to point into that I want to point to in the paragraph. The first one is, let's see, I'm trying to parse through the text as quickly as possible. It's this particular point, which means we're dealing with the following. If we imagine a series of city blocks, what this text is saying is Perry the platypus, the antagonist in this case, can't travel like so. He would have to travel that way using only blocks. And I think that is precisely the setup for Manhattan distance over Euclidean distance. And that is also the explanation here, where you have to, or if you want to be accurate to the prompt, you would have to use through buildings, or there's no moving through or above buildings, there's only using roads. So you have to, the distance from one point to the next on that grid would have to be determined by horizontal and vertical movement, not by a straight line or by cosine distance in this case. Okay, so this one, feel free to read it. It's what it's asking is essentially, how do you train a model and test it? And it's meant to be a very straightforward test of your concepts. And I'll just draw it out. Let's assume this is all the data that I have available. Then all I have to do is do this. I take about 75% of it. It doesn't have to be 75%, but that is a common number to use. And 75% of it is going to be my training data. I'm going to train my KNNs model on this 75% of the data, and then I'm going to use the remaining 25% to test it. And because I know the classifications of the entirety of the data, then I'm able to evaluate how good is this model because I know the true classification and I'll have the predicted KNNs classification, and I can just double check how accurately is it predicting for this data. This one is, I'll cover this one before pointing you to the recitation. This one is a discussion that, albeit turned a little bit lengthier than I intended in my KNNs recitation video about k-fold cross-validation. That's actually the answer to this question. Where you have 50% of the data being training, and then you test it on the validation data, which is separate from testing. And then after you pick one value of k for KNNs. Let's say you want to use 2 nearest neighbors. So you train it on that 50%, and then you test it on validation data. And then you use 3 nearest neighbors. You train it and you test it on the validation. And of all those, let's say 5 nearest neighbors was the best performer. Then after you have that 5 chosen, you evaluate it on the testing data. That is in principle what this k-fold cross-validation is, and it helps the protagonist in this case find the most appropriate value of k in terms of the k nearest neighbors. In the case of k-fold, it's how many times to repeat the process, essentially. So that's it regarding k-fold cross-validation. As I mentioned, I discussed it a little bit longer than I had intended to in the first time I brought it up in the recitation. So if it's unfamiliar to you, if you don't quite remember it, then please refer to that recitation for more details on how it looks and how to do it. Okay, so let's see. Feel free to pause, read the prompt. I'm just going to jump straight in because I know this is a KNNs problem in which we're going to be asked to classify this point according to different values of k. And I'll feel free to read the footnotes in order to make sense of the footnotes earlier. So I no longer have the graph. Let me actually, if I projected next to in the other window or in the other view, I won't be able to draw in it, so I'll zoom up and down accordingly. So we're looking for k equals 2, k equals 1, 5, and 11. So let me do the following. Let's say this is k equals 1, right here. Then k equals 2. So this could be, whoops, not that set. Apologies. It would be this one. This has shorter Euclidean distance to the point. And then let's go for blue. K equals, was it 5? Yep. K equals 5, then I have to choose. I'm going to highlight individual points. 1, 2, 3, 4, 5. But in reality, these 4 points are equidistant. So the choice of which of those are used as the nearest neighbors and which one isn't is a bit ambiguous. But what we do know is there are more nearest neighbors that are h for k equals 5 than for s because there's only one of them. Which means for k equals 5, this would be the surrounded area. And then for k equals 11, let's see, how many points are there? There's 11 points. So this would be k equals 11. Now to go back down, I hope I remember so this was S. I remember there being a point right there. I think now is a good time to bring up the side view. Yep. So k equals S. Then for 2, I had S and H as nearest neighbors, which means I couldn't tell because there was an equal number of both. There are more H's than S's within a k equals 5 range of the mysterious point. And in total, because I circulated the entire space, I just have to count here 1, 2, 3, 4, 5 S's. Did I count that right? 6 S's and 5 H's. So this is S. And now we're going to be asked to determine whether that was overfitting or underfitting. K equals 1 is overfitting in its clearest expression because the mystery point in this case is very clearly in an area just staring at it, you would think, oh, a point that falls in there is an H. Yet, because there's an outlier right in the midst of those H's, then the new point was considered an S. So it's sensitive, in this case the algorithm is sensitive to outliers. And k equals 2 is the same thing. Even though we couldn't determine the classification, that's actually precisely the problem. Because an outlier made the classification ambiguous. We couldn't decide whether it was actually an H or an outlier or an S. And you know, this sensitivity to the power of the outlier is what we consider overfitting. Then for k equals 5, intuitively staring at the graph, we can agree points that fall inside the area of H's or surrounded by H's should be H's. So that I wouldn't consider either overfitting or underfitting, but what I would is this one, because there the algorithm saw, as you saw me, I circled the entire space of points and I just counted, are there more S's or are there more H's in this space or this hypothesis space? And there were more S's, therefore any point that falls within the space is going to be considered an S, because the majority class is S. And that's what we call that the data is smoothened too much, because we're only paying attention to the majority class. Then here, it's what would happen if we changed one of the S's to H's. Well, in that case, the classification for the mystery point would still be, or would not be an S. It would change to an H, which is arguably correct. If I were to tell you, oh, that point was actually an H, then yes, it would be correct, but the effect is still the same. If I had a point in the midst of the S's with this new setup, it would be classified as an H, which is incorrect, and that's in large part due to the data being too smoothed. And so now we get a very standard type of problem, which is, let me switch back to the large view, which is essentially to draw the decision boundaries for, I forgot to just cue pausing and reading the prompt. So the decision boundaries for a k equals 1 nearest neighbors problem. And what I'll do is procedurally, I'll highlight the pairs of opposing points in gray, and then I'll start introducing perpendicular bisectors. I won't highlight absolutely all the points or all the pairs, just because of, I don't want to fill the entire graph with gray highlighting. Now I'll add the perpendicular bisectors in black. Here's one, another one here again. Okay, so we have those. And now I'll just extend all the lines. And this one actually, I believe, is a bit simpler than the one we saw in recitation for the first time, or the first time we discussed this. Let's see. Here I extend this. Whoops, sorry about that. And then these two connect here. And these are all pointing toward the same spot. So I'm going to have them meet in the middle and extend out of the graph, because these are decision boundaries. And that is the extent of this KNNs with k equals 1 problem. So this is actually not just the extent of the KNNs k equals 1 problem, it's the extent of the KNNs problem. So in the following part, you'll see I'll be talking about ID trees. Okay, so I'm back and we're off to the races with this ID trees problem. Go ahead and read the graph, or the prompt. I'll be projecting for a lot of these the table right next on the left hand side or on the right hand side, whichever way the video projects it. And I'll be projecting the table of classifications and features so that you have an easy reference as I work through the problems. So don't feel the need to memorize it or write it down. Okay, so now we have a very cheesy pun and a question asking us to calculate the average test disorder. So what I'll do is allow me to get set up here with the table. It'll be convenient to have it on hand. Wrong one. There we go. Okay, so first we're asked for the type of milk. I'll just, I'm still in orange. Milk. Test. And it's either cow or sheep. And as I'm reading here, there are, for cow, there's high, I'm reading off the popularity column. There's high, low, high again, medium, and then high. So that's a very mixed bag of a test. And then for the other one, we have, for sheep milk, we have low and medium, 2 mediums. So we have quite the set of calculations to make. First, I'll calculate the disorder for cow. So I have to calculate the branch. I think it's a good point first to review the equations. So the disorder of a branch is equal to the sum, the negative sum, I should say. The minus of the sum of the, not log, it's the number of points of a particular class. I'm just going to write y over the number of points over in the branch, and then the log base 2 of the number of points in a classification over the number of points in the branch. And that's a bit crammed. I hope you got all of that, hence why I also said it aloud. So the average test disorder then is going to be, for all the branches, the number of points in the branch over the number of points in the test times the disorder of that branch. So if we're calculating the disorder of the branch cow, we have first, let me make the negative here. Negative, whoops, not negative anymore. We have, I'm going to start with high, 3 over 3 points in high in class H over 5 points in that branch, and then log base 2 of the same fraction, plus, let's see, there's one in medium and one in low, so that's plus 1/5 log base 2 of 3/5 plus 1/5, whoops, not 3/5, 1/5, and then 1/5 again, log base 2 of 1/5. So that's the disorder of cow. Now for the disorder of sheep. Whoops, last bracket. Negative. And this one should have at least fewer terms. I'm going to start with medium and then low. 2/3 log base 2 of 2/3. Yep. And then plus 1/3 log base 2 of 1/3. Because one low point and 3 points on that branch in total. And so the average test disorder is going to be, I'm going to use variables in order to avoid writing the entire expression again. For cow, they're in total 8 points, if I'm not mistaken. Yes. So cow has 5 out of the 8 points in the test times disorder of cow. And then disorder of sheep has the 3 remaining points out of the 8 times the disorder of sheep itself. And I'll just write down approximately the answer so that you may practice this on your own. It's 1.20 approximately if you work out all the log terms and all the fractions. Now for firm. Firm, either yes or no. I'll just start reading off the points on the table I have on the side. For firm in yes, I have 1, 2, 2 high and 2 medium. And then in low, I have, or in no, sorry, not firm, I have 1 low, 1 high, and 2 highs, I believe, and who knew reading off a table would be this hard? This is no, so I have 2 lows, 1 medium, and 1 high. There we go. Okay, and so you should normally I see such an arrangement. In the case of the yes column, I'm going to start with a yes column in calculating the disorder. And when the disorder is perfectly, or when a branch is perfectly heterogeneous, so it's split half and half between 2 different classifications, then I know the disorder is 1. In this case, there are, so usually, and as I mentioned in the recitation in ID trees, I should have brought this up earlier, the disorder, if we're talking about a binary classification, so if we were talking about is popular, isn't popular, the disorder of a branch would be upper bounded by 1. That's the max value. But because we're talking about 3 different classes, high, low, and medium, then the disorder is no longer a max of 1. That's why we have an approximate 1.20 disorder calculation in part A for our type of milk. So that's why I'm going to calculate the disorder for yes, but when I see half and half split down a classification, I tend to think this is completely fully disordered, so it has a disorder of 1. But I'll verify, it's important to verify this with the numbers. Okay, so let me start applying the formula. It's negative 1/2 log base 2 of 1/2 plus 1/2, or 2/4, I should say more precisely, log base 2 of 2/4, as in 2 high, 4 total points, 2 medium, 4 total points. And so those are 2 equal terms, so I can just sum them. This is negative log base 2 of 1/2, and that I can also break down into negative log base 2 of 1 minus log base 2 of 2, and log base 2 of 1 is 0, log base 2 of 2 is 1, so this is equal to negative of negative 1, so it's just 1, as I suspected earlier. So now for the disorder of no, let me grab some water. The disorder of no then is, I'm looking at the table again out of habit. Negative, this is 2 out of 4, log base 2 of 2 out of 4. I'm thinking about lows first, then 1/4, thinking about medium, log base 2 of 1/4 plus 1/4, high in this case, log base 2 of 1/4, close bracket, which is equal approximately to negative 1/2 log base 2 of 1/2 plus 1/2, because I have 2 equal terms, log base 2 of 1/4. And then the average calculation is going to be, I'm going to have to rely on this white space at the bottom. Because the points are equally split across both branches, 1/2 times the disorder of y, which is just 1, plus 1/2 the disorder of no. And it works out to be 1.25 if you work out all the numbers. So you can use this to practice and to verify that you have the correct, that you have the technique down and the theory down. Okay, so onward. Now we're asked, I forget to stop at the prompt. Once you read the prompt, you'll see that we're asked to perform a greedy search, or to construct a greedy ID tree, which means we're always going to pick the test with the lowest average test disorder. And that's going to involve seemingly a lot of calculation, but in reality, many times you don't really have to calculate it in order to know the answer. So let's start, for example, we're told that we're starting with mold. So even whether it was the lowest test disorder or it wasn't, it doesn't matter, we're starting with it. So to classify mold, or to filter the points initially, we see that mold for yes has 2 lows. Just confirming to make sure. And then for the rest, we have the following data. We have 1 high, I'm reading from top to bottom, 2 highs, 3 highs. Yeah, 3 highs and 3 mediums. So this is our new data set. And and I'm going to borrow this data set. So let's see where I'm going to write it here. Medium, 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 high, high, and high. And I need to conduct 3 tests. The type of milk, whether it's firm or not. So the 2 for which we calculated disorders earlier, and then the age. Type of milk, either cow or sheep. Firm, yes or no. And then age. We're asked to split it into either, what was it? Low or high. So we've already calculated milk and firm, and I'll notice that the new data set, it's exactly the same, except I no longer have cheeses with low popularity. So I'm going to go back up to my calculations and see that milk had a low in each column, and then one of them was 2 mediums. Sheep milk had 2 mediums and 1 low. So sheep has 2 mediums and 1 low, but I'm no longer dealing with the lows thanks to the mold test, and the remaining points go to the cow branch. So this would be the remaining medium and 3 highs. That amounts to 6, I believe, yeah. Now for firm, same thing. I'm going to go back up, and in one branch I had 2 lows, a medium and a high, and then on the other branch I had 2 highs and 2 mediums. Was it yes and no? Sorry that I'm zipping around all over the place. Yep, on the no I had 2. Okay, so now for age, this is where I'll have to get cracking at a new one. For age, in low, we have only 2 data points, 1 medium and 1 high. If I'm reading correctly. And that means the rest, the other branch, is 2 mediums, 2 highs. And now just staring at it, I can choose the best classifier. And you would ask how, without calculating any disorders or average test disorder. It's, I'm going to highlight all the perfectly heterogeneous branches. Here's 1 medium and 1 high, so perfectly split across two classes. Here as well, 2 versus 2, 1 versus 1, 2 versus 2. And that's not the case in the milk. So for the milk, this is perfectly homogeneous, so disorder 0. And this isn't perfectly homogeneous, but it's not it's not a disorder of 1, because there's more of one class than the other. So milk is the clear winner here, without any sort of calculation. And if you're worried about eyeballing these things, it's perfectly good reasoning to just calculate the disorders, and you'll be able to validate this. And I think it's good practice as well to calculate them anyway. So we have milk. And I'm just going to put the homogeneous branch toward the left. So sheep milk over here, which is 2 mediums, and then cow milk over on the right. And I have the following new data set. It's 1 medium and 3 highs. And I need to find a new best test. So now I have, well, let me write the data here. 1 medium, 3 highs. Now I have just firm and age. So for firm, for yes I have, see, 2 highs that are cow milk. And then suffice to say that for no, the remaining points. For age, low versus high, I have of the low age cheeses, I have that are not low popularity, that rules out quite a few of them. There's only one that is cow milk that has a low age. So there's one high. And of those that are old, that are cow milk specifically, there's medium, or there's everything else essentially. I'm double checking the table because as you add as you add more of these tests in a row, it becomes a little bit harder to filter out exactly which ones you've selected, which ones aren't. I mean, of course, I can just go back up and highlight the rows, but it's not, technology-wise, it's outside of the scope of this recording. But that's what we have. And also looking at this, if I'm thinking in terms of average test disorder, both of these have a homogeneous branch. Whoops. And now let's think. Let's say, assume that even though it's not true, this MH branch of firm would have a disorder of 1. This one wouldn't exactly have a disorder of 1 because it has a majority class and it's not perfectly distributed. But notice how the homogeneous branch in firm has 2 data points. In age, it has 1. So the homogeneous branch in firm is going to bring down the average test disorder a lot more significantly from that of the age test, just by a mere virtue of having more points and therefore classifying more points, or helping us sort through more points at the same time. So I'm going to pick firm. Again, you may validate this on your own independently using the formulas, and you'll see that firm is the one with the lowest average test disorder. I've already forgotten. Yeah. Okay, so it's a yes on the right branch with 2 highs, I believe. And then on the no, I have 1 medium and 1 high. And I only have 1 test left, age. And that will bring me to, so low age, high age. The low age already perfectly classified 1 point as high, and then on high I would have the last point, medium. And that is my greedy ID tree. Okay, and now we're given 2 points and we're asked to use the ID tree, the greedy ID tree that we just constructed, in order to classify these 2 points. Let's see. So thinking back to the point, I'll go back to the ID tree after reading the first the Wagasi entry. So it's cow milk, it's not firm, and it doesn't have mold. Cow milk, not firm, low age. So it's not firm, it's cow milk, not firm, low age. That's high. And then for, I won't try pronouncing it, the Greek cheese, I'm assuming it's Greek. You may crucify me in the comments for saying that if it's wrong. Let's see, it's cow milk, it's firm, we don't know its age, and it doesn't have mold. I'll use a different color for highlighting. Doesn't have mold, it's cow milk, and I believe it was firm. Let's see, yep, it was firm, which means it's correct, it's a high. Just to double check, yep, it's high. And so we've successfully used our greedy ID tree algorithm, or we've successfully run the greedy ID tree algorithm and used our greedy ID tree. Okay, and I believe this might be the last question of this part of the ID trees. It's assuming you've read it already. We're given a new feature, vegan, and we're asked whether we're able to, whether it's useful basically, or whether it would change anything. And I think the answer, we can see it almost reading off the table. No, and the reason is, let's say I added a new vegan test. It would look like this. No, because there are no yeses in the data that I have available to me, and the resulting branch would be high, low, low, high, 3 mediums, and then high again. So it's done absolutely nothing to classify the data that we have in any meaningful way. It's essentially repeated the data that we had without any sort of change. And so if I were to add this to the greedy ID tree algorithm, it's the same as just not adding it because it's not contributing anything. And that's mainly the logic of why this wouldn't change, or that's mainly the explanation to fill in this box. Is it's a single branch, so it doesn't split the data along any meaningful feature. Or that's why the feature is not meaningful to this data. And that is the end of the greedy ID trees. And for the next section, I'll be talking about I'll be going through the neural networks problem. Okay, we're back and ready to apparently not ready to take on neural networks. As usual, read at your own time. I'll just go ahead and go through with the question. Wherever necessary, I will, it's already necessary, so let me prepare the side view and project it. Let's see, there we go. So we're just asked, what do we need to perform forward propagation through the network? And so first I'm looking at calculating the output of the neuron A at the top, and I see that it is just the threshold function that we are given here applied to weight 1 times the input x. See, and that's correct, just verifying. And the threshold for this is out B, is the threshold applied this time to weight 2 times output X, or input X, sorry, and weight 3 applied or multiplied by Z, input Z. And now we're asked to calculate the final output of the network, and I'm going to use, as the instructions permit, out A and out B, just so that I don't have a mess of terms. So out C is equal to, again, the same threshold function. We're assuming they have the same threshold, or not the same threshold function. And we have W4 in order of the number of weights, or the weight number, W4 times input Y, plus W5 times out A, plus W6, W6 times out B. And that is the output of the network. Fairly straightforward. Now we can move on to a more complicated problem. And I apologize in advance for this problem. It was an oversight of ours to rely only on colors instead of different shapes for the points. But the prompt talks about green, yellow, and red points. If you have trouble seeing color, then I'm just going to delineate here the different areas. So these points are all yellow, these points are all red, and the points in here are green. So now that I have that, we're going to be building the following neural network using the equations above and the classification areas that were given. Okay. So my approach generally is to extend the lines. I'm going to use the boundaries I just drew here because these are the different regions. And if I'm trying to, my approach here is I want to understand what is at play here before thinking about the specifics of the neural network. And what is at play here is there are 3 lines, so I'm going to need at least 3 nodes, or 3 input nodes, and it seems that only the overlap of the 3 lines is where green is the area of interest, which means I'm probably dealing with an AND node at some point. And so now that that's my rough approach, or not approach, that's how I'm thinking about this problem. Now I'm going to write the equations of the lines, not necessarily deal with the thresholds just yet. So the equation of this line is y equals 1. This line it's a negative slope, and the y-intercept, actually the slope is -1, so that's convenient. The y-intercept is 5. And I believe this line is symmetrical, except the slope, as in it's the positive slope, but same y-intercept. So it's y equals x plus 5. And now that I have the equations of the 3 lines, I can start converting them or writing them in a more useful form when I'm filling in the values for the neural network. So this y equals 1 equation I can rewrite as 0x plus 1y is equal to 1, and because I want everything that is above that line, I want this to be greater than or equal to 1. Now thinking about the rightmost line, y equals negative x plus 5, I can rewrite it as x plus y is equal to 5, and I want everything that is below and behind the line. So this is x plus y is less than or equal to 5. And because we're dealing with thresholds that are greater than or equal to, I'm going to rescale by -1 so that I flip the inequality. Negative x minus y is greater than or equal to -5. So that's my first thought. And for the other one, let's see. Let me catch up to my own notes. So this is negative x plus y is equal to 5. And this one actually is I tried to catch up to my own notes because it's a little bit tricky whether I would do greater than or equal to or less than or equal to 5. And we can almost, actually, I'm not going to say whether it's greater than or equal to or less than or equal to. I'm going to figure it out by using the other two lines of which I am sure of their inequalities. So I have those three equations. Let's start first with this one. 0x plus 1y is greater than or equal to 1. That's an easy one. So I see that threshold 1, so that this is where I'm looking. 0x plus 1y is greater than or equal to 1. Yep. Okay. Then what's next? I'm also sure of negative x minus y is greater than or equal to -5. Okay, so we're thinking of, whoops, I miswrote 0. Okay, negative x minus y is greater than or equal to -5. I know it's negative x, so this one isn't it. So it must be this one. But it's -10. So I could technically just rescale by 2. What's to stop me from saying -2x minus 2y is greater than or equal to -10? It amounts to the same threshold. So I'm going to say -2x, -2y. There's a minus already there. I keep mixing up the weights. No, actually, this confirms what I was thinking. So it's -2x minus 2y, -10. It's the same equation, just rescaled. Okay, and now we have a 1 here, nothing for y, and an empty threshold. I know the threshold has to be greater than or equal to, and I have a negative x, which means which implies then I need to multiply by -1, which would flip the inequality if I were to make it greater than or equal to 5, which means the process would be this turns into -x plus y is less than or equal to 5, and that corresponds to being below this line. So we want the sum of -x and y to fall in this area. That's what the equation less than or equal to 5 is saying. And I know it's confusing to think about, which is why I wanted to argue, okay, I'm going to figure it out by looking at the neural network. And now I'm going to multiply by -1. X minus y is greater than or equal to 5. And so here's the 1. Oh, sorry, not 5. -5. Here's -5. And this is -1. And what we do is, let's test it. Let me scroll down a little bit on the graph over here. I don't have the annotations for the colors yet, but so I apologize for that. Anything that falls outside the triangle needs to have an output of 0. And yes, I haven't addressed, actually, let me address the outputs, the weights in the last layer. So I have a threshold of 5 over here, and I have 3 outputs, and I want the result to be an AND of all the neurons. So this is getting into solving the AND function in the neural network recitation. But I want some number or some weight that when sum 3 times is greater than 6, when sum 2 times is greater than 5, when sum 2 times it's less than 5. And I think that number is 2. So 2, 2, and 2. I didn't see that I had a 2 already there. So the neurons A, B, and C are going to output a 1 when their threshold is met and a 0 otherwise. So I'll have 6 when all three neurons output 1, and that means something has fallen within the triangle the way I've written these equations. So let me grab some water. Okay, and now let's just test a couple points. Let's test 0, 0. That should be an easy one. Then 0, 2. Or, yeah, 0, 2. That should be a 1. And 3, 3. 3, 3, just to test one side. -3, 3. And I can test these fairly quickly. I encourage you as an exercise in forward propagation to test those points I've written down in order to ensure that this is the correct solution. Okay, so here comes a tricky one in reality. So this one had multiple answers. The one I found were deleting weights such that the red points are also green. So we essentially want all of this to be classified that way, and that's actually how I think about this question. Now the area of interest is this, which means, if I'm thinking about it in terms of the graph, whatever I want the AND of this in the graph, no longer the AND of the triangle. But we can't, let me delete that. We can't change the threshold. So I can't change the threshold to make only the first 2 firing be enough. And that's one hack that I'll apply here. So we have the following setup. Right, and the threshold is 6, and these have a weight of 2. Or the threshold is 5, sorry. Which means if I were to delete the line entirely, if I were to delete this, I wouldn't be able to meet the threshold, because there would be only an input of 4 if the other 2 lines said, okay, then this is good. But let's go back. See the threshold. I didn't mean to do that. the threshold is -5. And what that means is, I forget the drawing is right here, I think. No. The drawing is here. Oh, so it's fully connected. I forgot. So this is the first hack. Let's say this neuron didn't get any input. Let's remember its threshold is 5. So let me delete this and delete this edge. So the input to this neuron is 0 now, and its threshold is -5, which means when there's 0 input to neuron A, the threshold is met and it outputs a 1. So we're offsetting. It's almost as though we're offsetting the other two by a uniform value of 1 multiplied by 2, the weight of neuron A. So one solution is to delete W1, I believe that is. Let's see. W1 and W4. So yes, it can be done. And I encourage you to consider what would happen if you only deleted W1. So let me write in some neutral color, blue. What if you only delete W1? Meaning the neural network would look like this. Well, let's think about it briefly. So this is -1, and the equation that led us to that was x minus y is greater than or equal to -5, which would imply the original equation being y is, or -y is greater than or equal to -5, if I'm not mistaken. So if I multiply that by -1 across the board, y is greater than, or y is less than or equal to 5. And where is that? That is here. So we would have an AND of this region and the other two lines, which is technically it is what the question is asking for, because we asked, let me delete some of this junk off the graph, because we did ask for this region specifically, nothing above it. So technically it is correct. It's a more sane answer, if you will, because I will be the first to admit that deleting the weights and arguing, oh, neuron A has no input, therefore it's a uniform offset for the other two, that's, I'm going to say, pretty hacky. And that's just the first solution that I thought of. The easiest one, but perhaps the one that required a different way of thinking about it, is just delete the x component, weight 1. So delete weight 1, and that should cover exactly the area that is red points on the graph. So the way I was thinking about it was everything that's even off the graph. So that's, depending on how you looked at that question, then would have been this approach, just W1 or W1 and W4. Okay. And I think that's enough with regard to building neural networks and deconstructing them. Now on to the last part of neural networks, which is backpropagation. And we have again, I'm moving, yep, adjusting the graph. This is, we have the same graph now, and or the graph we had at the beginning, and now I trust you for the prompt, and I'll just start working on this problem. So I'm asked to list the inputs x, y, z, and outputs and weights, all the terms essentially that I need in order to compute a new weight, a new W2. And my approach to these is, if you remember, I think if you don't understand what I'm about to do, a very helpful video I think would be not the recitation video on neural networks, but the chain rule video on neural networks. I think I titled it Neural Networks Office Hours. So that one, I think, is where I develop, or where you can develop the intuition of these are the terms that I'm going to need for this particular calculation without having to solve it. So I'm asked to calculate W2. And the intuition is I need to know how W2 influenced output C. So definitely I need output C, and I need essentially anything that led from W2 to output C. So I need W6, I need out B, because W2 influenced out B, and out B influenced out C with W6, and I need the input as well. And so that is actually the list of terms that I need for this calculation. So I need X out B, well actually in order from back to front, X W2 out B, whatever the weight of out B is, W6, and out C. So those are the terms that I will need in order to calculate a new weight for W2. And in this case, W2, as I've written it, is whatever the value of W2 is right now, because that obviously influences what the new value will be. And now we're actually asked to calculate this. And so this is going to be a combination of using the formulas that are in the recitation handout and the neural networks recitation handout, and are in the recitation itself. So I'm just going to mechanically move through how I would go about putting together the equation. So I know W2 new is equal to W2 old. That's a bad place to write it. Aka W2 in this question, plus a delta W2. So how much the old value plus some term that tells me by how much to change it and in which direction. So I need to calculate now delta W2. And that is equal to the learning rate R times the input to the weight, or the input that went through the weight, to put it one way, and delta B. So this is where out B, where we're starting to calculate the influence of W2 on later neurons. Let me get my hair on my face. Then I need to calculate delta B. And if you remember from the equations, it was the derivative of the sigmoid function, which is out B. Well, the derivative of the sigmoid function with respect to the input, if I'm not mistaken. The more details on that in the rest of the office hours neural networks video that I mentioned. Out B, 1 minus out B, that is the derivative of the sigmoid. And then with respect to, let's see, And then in the problem is, the problem I'm struggling, you'll see it yourself in the neural network soft SRs video. The deltas don't exactly match up the terms that I would call the deltas in the back and the chain rule derivation of this equation. So because they don't exactly line up, I hesitate to call them one way or the other. But this equation in particular is given in the recitation handout. So you'll have a clear-cut answer to, or a clear-cut equation to use in this case. And the equation is in fact out B 1 minus out B, and if delta B is not an input neuron, or if neuron B is not an input neuron, which it isn't, you have to multiply that by the sum of the deltas of all the outgoing neurons times the weights that connect the out B to the outgoing neurons. Thankfully, there's only one, neuron C. So let me erase this and just write here W6, let's see, yep, W6 times delta C. And now I need delta C. And delta C is equal to, remember that now we have the condition delta C is an output neuron, so the equation is a little bit different, but it starts the same as when the neuron is not an input neuron, or is not an output neuron. So it starts with the derivative of the sigmoid function, or the sigmoid threshold function, out B, 1 minus out B, not out B, out C. Minus out C, and now because it's an output neuron, we have the derivative of the loss function, and that is out star, so the output that we wanted originally, minus out C, the output of, so the real output, or the desired output, minus the output of the network itself, which is out C. And if you put all the terms together, you get the weight update equation for the for W2 new. So how to update the W2. And last but not least, we have some conceptual questions on neural networks. I believe that's no, sorry, that isn't the last question, but we're getting there. I trust that you've read the equation already, or the prompt. Now let's talk through some of these concepts. If a training is taking too long, generally the problem is that the learning rate is too low. So if the landscape, this is in reference to the neural nets recitation video. If you don't remember this, please go back and watch that. If the loss landscape looks like that, I believe this was the graph, and you're moving too slowly, then increasing the size of the jump will obviously speed things up. So increasing R will help. So number 2, model's chosen weights are causing its neurons to output only zeros. The problem with that is that it can be attributed to any number of things. It could also be that the neural network is simply designed poorly. So I'm going to say none, because it's likely not an issue with learning rate. There's any number of things that could have gone wrong, and learning rate isn't necessarily, a learning rate is about how fast or how slow to get to an answer, minus some caveats. So it's not about the answer itself, mostly. His weights are unstable. So that typically can be solved with decreasing, and what is meant by weights being unstable, I'm going to reuse this graph at the bottom. No. the weights being unstable means, let's say it was here, and then it jumped to over here, and perhaps it jumped to over here, and then again jumping to over here. So it's jumping all over the landscape. And one way to mitigate that is to, did I already answer it? Oh, decrease R. Yeah. I forgot I was explaining the question I just answered. Okay, and then the last one is weights converging on a local maximum. And that means assuming, I'm going to say it's converging here instead of maybe here. So this is what we want, this is where we are. The reason is, if the learning rate is too low, it's going to be stuck here because it's going to, the learning rate is going to keep it in this area where the slope is going to tell it just adjust and stay at the top of this hill. But if you make a large jump, then you end up maybe here, or actually where that point is right there, this one. And so that'll change the slope and make you go up, and perhaps you'll end up here, but now you're at a hill that is higher than where you were before. So increasing the learning rate helps with local maxima, but it's obviously a balancing act, because if you increase it too far, you're going to be unstable, and it's not necessarily a universal solution either. But it's a good approach, or it's a good start. And last but not least, actually this time, is we're asked to answer whether this this neural network is capable of solving the following problems. And I'll remind you that in the recitation video where I had this set up, I was able to solve sorry, oops, I was thinking of the wrong neural network. The majority of these problems, I was able to solve them with this particular neural network by drawing a line here, or by drawing a line here, or by drawing a line here. So I know that, and I know this smaller neural network can be very easily approximated by this larger one, because all we need to do is set some thresholds or some weights to 1 or to 0. And we get the, for example, I could just, let's see, set this to 0, set this to 0, this to 0, and set this threshold to 0 or to some other low number, and I would get the same behavior as this neural network. So a neural network being larger than another one is not a problem. Which means, and what I want to say with that is that if this neural network solved not XOR, sorry, an AND, then this larger neural network can solve it just as well. The problem came with XOR, and the reason was this small neural network can draw the following lines. It can draw this here, and it can draw this line and a vertical line, but it can't draw two lines and shade them. And that's where the other neural network that I drew came in. I'm going to redraw it here. This neural network was able to draw two lines and shade this area correctly. But now we're looking at not exactly this neural network, we're looking at a cut down version. So we're looking at this. And what that does is, let me delete this shading. each neuron here was drawing a diagonal line. But now one of the lines is fundamentally limited because it doesn't have a input from the x dimension. So take a look at this pair. This can only can only represent equations of the form y is greater than or equal to something. I'll just write this. Which means, let's say the bottom neuron was the one drawing the bottom line. Now I only have access to lines of the following way, this. So I can draw one diagonal line or one sloped line and one horizontal line. And what that means is I can no longer solve the XOR problem with what I have, because I needed these two lines to be able to solve the XOR problem. And that's the full explanation of why this cannot be solved by the given neural network. And that brings our review session for KNNs, ID trees, and neural networks to a close. I hope this was helpful to you, and obviously I couldn't go into detail in many of the concepts as I would have wanted, but the other videos are still available, so feel free to reference them should you need any help, and I'll see you on the next one.